So now that we know that alpha and beta form are in equilibrium with open chain structure, we discuss a property that we have right in front of us called mutarotation. Now, if we take, let us say, the alpha form, and we know that the alpha form is in equilibrium, so it is in equilibrium with beta form. Now, if, for instance, that I have my specific angle of rotation in alpha form as 112 degrees, and in beta form we have specific angle of rotation as 19 degree. So when this alpha form having a specific angle of rotation as 112 degree will try to go towards equilibrium, and this 19 degree of beta form will also try to attain equilibrium. So we have both of them approaching equilibrium. Now at equilibrium, the angle of specific angle of rotation is 52.5 degrees. Okay, so now this is the specific angle of rotation at equilibrium. So our alpha form as well as our beta form try to approach it. And when we start with, let us say 112, it slowly moves on to 52.5 degrees. And also, if we start the beta at 19 degree, it slowly moves on to 52.5 degrees. So both of them are trying to reach the equilibrium specific angle of rotation. Okay. Now, what is specific angle of rotation basically? If you're familiar with it, so specific angle of rotation is the angle of rotation produced. So specific angle of rotation is the angle of rotation produced to plane polarized light by the solution. So whenever I have a plane polarized light and I pass through it through my solution, the angle of rotation produced is known as the specific angle of rotation. So just writing that the angle of rotation produced to plane polarized light by the solution. Okay, so this is my specific angle of rotation, and 52.5 degree here is my angle of rotation, specific angle of rotation at equilibrium. Now, both the alpha and the beta form are trying to attain the equilibrium specific angle of rotation. So now, if let us just assume that alpha form, say my alpha form was, let us just keep it at x%. So if my alpha form was at x%, the beta form will automatically be 100 minus x%. So now we're trying to find the percentage. So our theta effective, that is the effective angle, will be x into 112 degree, because that was the specific angle of rotation for alpha, plus 100 minus x from beta, and beta is at 19. So if we divide this by 100, so what we get is theta effective comes out. So this is equal to 52.5 degrees because it is at equilibrium and they are trying to attain equilibrium. So when we solve this, what we get is that x comes out to be 36%. Okay. So if my x is 36%, let us just now say that I assume that alpha form and beta form were in equilibrium. Okay. So our alpha form was, we found that it was 36%, and beta form was 100 minus 36. So it automatically becomes 64%. So now we have alpha and the beta form, their respective percentages. Now this specific angle of rotation, what we have studied is it is equal to theta upon c into L. That is one formula for it. And this theta is the angle, okay, that we just calculated. Okay, so if I have the percentage of alpha at 36% and the percentage of beta at 64%. So with the help of this, we can find our K equilibrium, that is the equilibrium constant. And what is our equilibrium constant now? So my equilibrium constant actually becomes 64% divided by 36%, and that leads to our equilibrium constant. Now, what else? Since this beta form has a higher percentage, so we can just say that beta, and we know that beta is more stable than alpha form, having previously done it. Okay, so beta is more stable than alpha. This further proves it that beta is in fact more stable than the alpha form. So this K equilibrium we get when we divide 64 by 36, and from K equilibrium we can also find the value of delta G naught, which is nothing but minus RT ln and equilibrium constant. So we get a number of values from knowing these alpha and beta form percentages. Okay. So what we have done just now is rotation. And if we are to put a specific definition onto it, so specific angle of rotation, now this explaining, now we are explaining rotation. So specific angle of rotation changes with time. This is what we observed, that the specific angle of rotation was changing from alpha, which had 112 degree and was coming on to 52.5 degree to attain equilibrium. So specific angle of rotation changes with time till equilibrium is obtained. So the main motto or the main goal is to attain equilibrium. So till equilibrium is attained. And this is nothing but what we wanted. So this is rotation. So this is what is known as rotation. That the specific angle of rotation changes with time. Its rotation changes with time till equilibrium is attained. Okay. Now, what else? So I can just see here that my theta effective, that is the effective angle of rotation, it varies, and at equilibrium the alpha and the beta become constant. Okay, so what am I trying to tell you? That the theta effective, so when we see that the theta effective, that is this 112 and this 19 degree here, is not constant, so they are varying, but when they are trying to attain this equilibrium, and at equilibrium they become a constant. So they, at equilibrium, they reach this 52.5 degree here. Okay. So now theta effective becomes constant over time. So we can say that theta effective is nothing but a function of time. So we can just write that theta effective is nothing but a function of time, and I represented it something like this. Okay. So we have drawn another conclusion from all this, that theta effective is a function of time. And here this time t will be nothing but less than time of attainment of equilibrium. So it is that time till I attain equilibrium. Okay, so we have now seen that theta effective is a function of time, because with time the theta effective varies, and after a certain time, that is at equilibrium, it becomes constant. So it is reaching to a constant over time, so it is a function of time. And this time is less than the time of attainment of equilibrium. So this is all that we had to see in rotation.